Hi Level 3s and welcome back to 3.6 Aqueous Chemistry. This is Lesson 4, Part A. So what are the learning objectives for today? Today we're going to cover why ionic solids dissolve. So that's a recap basically back to year 11. We're going to describe dissolving in terms of it being endothermic and exothermic. We're going to write Ks expressions and we're going to interpret Ks values. Okay. So just remember what dissolving is. So there are two terms, solvent and solute, and they're very general terms actually how you describe these. So solvent is the substance that dissolves the other substance, which sounds a bit buzzy, but that's exactly what it is. So the solvent here in this picture would be, for instance, water, and the solute is the substance that gets dissolved. Okay, that's the easiest way to describe it. Now, the solute doesn't have to be a solid, it just most often is. The solute could also be a liquid dissolving into water, for instance, and that would form an aqueous solution. So that's solvent and solute. You've probably used those terms a lot over your lifetime in chemistry. So one thing to note is in chemistry, we're not going to worry about mass changes when you dissolve a solid into a solution. We're going to presume there's no mass changes because we add such small masses. That's just one thing to note. Okay, so ionic bonding, a bit of a recap what an ionic bond is. I know that you guys know this, but ionic bonds are formed from the transfer of electrons from a metal to a non-metal. So metals always lose valence electrons and they form cations, and the non-metal always gains electrons and they form anions. The actual ionic bond itself is the electrostatic attraction between the oppositely charged ions, okay? Now we know that every bond in chemistry is electrostatic, so it's always important if you're defining a type of bond that you mention the words electrostatic and state the positive and negative that are being attracted. So in this case it's the positive ion and the negative ion. And you can see an example here where sodium is donating an electron to chlorine, that becomes sodium plus chloride minus, and the attraction between these two is the ionic bond. So how do substances actually dissolve in water? So there's kind of three stages, and we don't actually cover this in this much detail at level 3. This is just me kind of showing you, because you've done Hess's law before, so you can actually understand that all of these energies can add together. But essentially, in order for something to dissolve, the ionic substance first has to separate into ions, and then they have to get hydrated with water. Okay, so bonds break within the solute. So solute, the solid that we're dissolving, is sodium chloride. The ionic bonds have to break. So the ionic bonds are those electrostatic attractions between the positive and negative ions. Okay, and this process of breaking bonds is endothermic. So it's got a positive value to separate the ions. That makes sense because you've got to put some energy in there to break the bonds. Bond breaking is endothermic. So that should be pretty straightforward. And then the next step is actually to hydrate them, which is when we define them as being aqueous. Okay, and so this is when the water molecules surround the ions. So if you've got your polar water molecule here, we know that the oxygen is slightly negative, the hydrogens are slightly positive. So the oxygens will surround the sodium ions because they're positive, and the hydrogens will surround the chloride ions, and that's what you can see here. Now this is called hydration, okay, and this is when you're actually creating forces of attraction between the ions and water. So you're actually making bonds here, and this aspect is actually exothermic, okay, where the bonds between the solute and the solvent being water, solute being the sodium chloride, that part is exothermic. So in order to work out whether this reaction is endothermic or exothermic, we have to take into consideration the energy needed to separate the ions and the energy released when they form hydrated substances. And if you actually compare the two, it ends up being ever so slightly endothermic. Okay, so overall it's ever so slightly endothermic when we combine those. You do this lattice enthalpy, by the way, all the stuff in a lot more detail if you take scholarship with me. Okay, so dissolving solids and liquids, based on what we just saw, I just showed you that it was ever so slightly endothermic, dissolving that ionic solid, and that is a general trend across solids and liquids. So solids and liquids, when they dissolve, are ever so slightly endothermic, okay, and so they absorb a bit of energy in order to turn into aqueous ions. You don't need to memorize this for your internal, but it's just important to understand that dissolving also has some energy changes, and that's why I mention it. So this stuff is not imperative for your external standard, but it's just good. The whole topic is about dissolving, so you should really understand that when you dissolve a solid or a liquid, it's a slightly endothermic process. So what about dissolving a gas then? Because I've just been talking about solids and liquids, so what about a gas? So actually a gas, you actually ends up releasing heat energy. It's an exothermic reaction. And the reason for that is to actually dissolve a gas, you must make forces of attraction between the liquid and the gas particles. Because remember, gas particles we define as being that there's no forces of attraction between them. So if you're trying to go from something that's got no forces of attraction between it to something where you're creating forces between the gas molecule and H2O, then you're making attractions, and therefore you're bond making, and so this process is exothermic. So this is quite cool, because this is just in real life. You can actually understand that if you dissolve a gas, energy is going to be released, and if you dissolve a liquid or a solid, energy is going to be absorbed. So what happens when we dissolve ionic solids? We've looked at this before. We looked at it on lesson 1, and I think that you'll all be fine with this now. When you dissolve an ionic solid, the only reason why this actually dissolves is because the attractions between the water molecules and the ions are stronger than the forces that are actually holding the ions together in the ionic bond. If the ionic bond was stronger, then it wouldn't dissolve. And that's the principle for all dissolving. And we can see that the positive sodium ion is surrounded by the negative oxygen atoms. Now, it's really important that it's atoms, because water is a neutral molecule. A really common mistake that I see when I mark this paper is that students will say that the sodium ions are surrounded by oxygen ions, and that's not correct. The oxygens are atoms inside the water molecule, okay? And the negative chloride ions are surrounded by the hydrogen atoms of water, okay? So just make sure you get that correct. And this is what they look like. A bit of an extra note is that actually naturally 6 waters will surround a sodium ion and 6 waters will surround a chloride ion, and so they're actually called hexahydrate, hex meaning 6. Again, you don't need this for your achievement standard. I just thought it was quite interesting to show you that certain ions can have a capacity for a certain number of water molecules, and in this case it's 6. It often is 6, but sometimes you can get 4 and so forth like that. So copper oxide is not very soluble, so it doesn't dissolve very much. And so why would that be? So remember, the reason why, if we go back a slide, the reason why sodium chloride dissolves is because the attractions of the sodium ions for water and chloride ions for water are stronger than the ionic bonds holding these together. So if something doesn't dissolve, that must mean that the ionic bonds that are holding the Cu2 plus ions to the O2 minus ions are stronger than the bonds that can form between Cu2 plus and H2O, or O2 minus and H2O. So the ionic bonds in this case are stronger, and therefore it doesn't dissolve. Does everything that dissolves forms ions then? And the answer is no, of course not. There's loads of substances which can dissolve into water and they don't form ions. And an example of this is sugar, which you've put in your coffees and teas and whatever. So sugar will dissolve and it doesn't form ions. It's just in this topic that we're covering in 3.6 aqueous chemistry, we're always focused on dissolving ionic substances, and so they will form ions. But it'll be remiss of me just to kind of not mention that loads of things that are solids can dissolve and they don't always form ions. Right, so we've spent quite a bit of time in the last few lessons talking about what a saturated solution is and what an equilibrium is, and just to reinforce one more time. Here, this is an equilibrium of solid silver sulfate. So if I was to dissolve solid silver sulfate into a beaker of water, I would keep adding it until I saw solid forming at the bottom of the beaker. And when I see solid forming at the bottom of the beaker, that tells me that no more will dissolve. And if no more will dissolve, then I have created what we call a saturated a saturated solution. And a saturated solution is one where equilibrium has been reached. Okay, so that's how we know equilibrium's been reached. When we say solid at the bottom of the beaker, it means we've reached saturation point and no more can dissolve. And so even though it looks like a clump of solid at the bottom of the beaker and nothing much is happening, it is actually a dynamic equilibrium, so therefore the rate at which the silver sulfate is dissolving is the same rate at which the ions are reforming together as the solid, which is pretty cool. Cool, so what is a saturated solution? So just in a bit more detail, saturated solution is the maximum amount of that solid or solute that will dissolve at that temperature. Okay, and so therefore if it's a maximum amount of substance that can dissolve, it therefore has a concentration, and this is critical. So solubility is a concentration, and therefore solubility has the units moles per litre. And so this is what we're focusing on today when we talk about all of this stuff. So what's going to affect solubility? How much of a substance dissolves, the concentration of those ions that can be produced in that solution? Because it's an equilibrium system, everything that we've just been covered about Le Chatelier's principle over the past 2 lessons, they will be the factors that will affect how much of a substance will dissolve. And you already know this because we've already done a few examples of this. So temperature will affect it, pressure will affect it, and concentration will affect it. So the same things affect our solubility equilibriums as every other equilibrium that we were looking at. Okay. So we've already recapped equilibrium constants, Kc, for an equilibrium where we do the concentration of the products divided by the concentration of the reactants. Well, now what we can do is we can actually change the name to solubility product, which is Ks. And that's simply referring to, instead of just a general equilibrium, we're now referring to a solid dissolving. Okay, so if you're dissolving a solid and you're doing so in equilibrium like this, so dissolving a solid into ions, then we can use the symbol Ks instead of Kc to represent that we're talking about dissolving a solid. So just as per normal, we do products divided by reactants. If you've got a number in front, it becomes to the power. So it's going to be Ag plus squared times SO42 minus. Now this time, we can't divide by anything. We can't divide by our reactants because our reactant is a solid. And we know that the concentrations of solids and liquids do not actually change because it's based on density, and therefore, which is a constant, and therefore we don't include our solid into our equilibrium expression here, into our Ks expression. So it just becomes the products. So let's go through some examples of actually writing some Ks expressions. So you can see here we're going to do Ks equals, and it's going to be Ca2 plus in square brackets cubed, because there's 3, times PO4 3 minus squared, and we don't divide by anything because it's a solid. Okay, so this is what it looks like. I hope that makes sense. I've actually included here what that Ks is, because some people, some kind people, have gone through and done all of the ionic solids for us and produced these Ks for us. So somebody's actually done the grunt work and told us how good every ionic substance is at dissolving in water. And we can see here that this is a very small Ks. And it's very small because it's 10 to the negative 33. And so if you get a very small Ks, what that tells us is that we don't have very many ions at all, because it's products divided by reactants. Remember, that's what it means. So if we have a very small number, we've actually got hardly any products, and that we've mostly got reactants. And if we've mostly got reactants, that means we've mostly got our ionic substance still intact. And if that's the case, that's pretty much telling us that calcium phosphate is not very soluble at all. And so that's what the conclusion we can draw from this entire situation. That if you have a small Ks, just like a Kc, it tells us the ratio of products to reactants. And so if we have a small Ks, that tells us that we mostly have reactants present. And if we mostly have reactants present, we mostly have the solid present. And if we mostly have the solid present and have very few ion products, that means the substance is not very soluble. So a small Ks means that that ionic substance is not very soluble, and a large Ks means that ionic substance is very soluble. Okay, I'm going to pause this video here and we'll be back for part 2 shortly.